All right, y'all. I'm a little sorry about my voice being a little rough today. I guess I just kind of talked myself out of a voice. But we're going to talk about titration. Some of this is going to be a review, some of it is going to be new. So when I'm doing a titration, remember that a known concentration, that is my titrant, of in this case an ester base, is going to be slowly added to a solution with an unknown concentration. And that unknown concentration is going to be my analyte. So my titrant is the one that I know. That is usually going to be in the burette. It's not always, but oftentimes is. And my analyte is what I'm trying to analyze, my unknown concentration. So as I look at this, another thing I want to think about is how can I determine whether I have reached the equivalence point? Remember, that's my important point in a titration. That's where I'm going to be at stoichiometric equivalence, where I've added enough acid to react with all of my base, or enough base to react with all of my acid. That means that titration problems really are just stoichiometry problems. And it means that a key step is going to be making sure that you look at the stoichiometry of your balanced chemical equation. You can either use a pH meter to see this, or you could use an indicator. We've done that before, where we're looking for the end point where the indicator changes color. And we want that end point to be just a tiny bit past the equivalence point so that we know we've reached equivalence when we see the color change. One thing to remember when we're talking about titrations is that the strength of the acid or base doesn't actually change the number of moles of H plus or the number of moles of OH minus. Stoichiometry does not care if it's a strong acid or a weak acid. If I have a 0.1 molar solution of HNO3, then I have 0.1 molar H's floating around dissociated. If I have a 0.1 molar solution of HNO2, because that's a weak acid, most of it will not be dissociated initially. But as I react the dissociated H+, Le Chatelier's principle says I'm going to make more products and more products. And so I'll be able to keep reacting and reacting and reacting. So stoichiometry does not care if an acid is strong or weak. It's going to use the exact same number of moles of base to use up the acid, whether it's HNO2 or HNO3, because they're both monoprotic acids. It's a really important thing to remember because that is almost always going to show up somewhere on the AP exam, and it's almost always one that a lot of people will miss because they'll think that a weak acid doesn't take as many moles of base to neutralize. That is 100% not true. Stoichiometry doesn't care whether your acid is strong or weak. So let's look at a titration of a strong acid with a strong base. This is a review from Unit 4. In this situation, I know that the acid solution is in the flask initially, and I know that because my pH is very low, which means that my probe is in an acidic solution. I must be adding the base because as the base is added, the pH eventually sharply increases and then levels off at a high pH, which tells me I've added plenty of base. Also, RT graph. It says I'm adding NaOH here. So my base solution is in the burette, and my acid solution and my indicator is in my flask. And I want to find this equivalence point. So I'll see when I do this, I get a couple of regions here. I get one region where I get this slow increase in pH as I have excess H plus ions each time. And in this region, I'm just doing a stoichiometry problem with a limiting reactant. All of my H's and OH's will be dissociated because I have a strong acid and a strong base. So I'll use up all of the base and I'll have excess H+. Then around the equivalence point, I see that very rapid pH increase. And the equivalence point will be in the center of that rapid increase. And that actually remains true whether we have a strong acid and a strong base, or a weak acid and a strong base, or a weak base and a strong acid. With a strong base and a strong acid, the pH at the equivalence point is always the same. Because in that case, my moles of acid initially present will be equal to my moles of base that have been added. That means I'm at equivalence. And that means the only thing left in my solution is water, and a neutral salt. Because my salt is formed from a strong acid and a strong base, that means it has extremely weak conjugates. So that neutral salt formed doesn't hydrolyze water, and therefore the pH remains the pH of pure water. So at a strong acid and a strong base, whether I'm going this direction with strong acid in my flask, or whether I'm going the opposite way, where I'm titrating a strong base and adding acid, in either case, the pH will be 7 at the equivalence point, because I'll be making water and a neutral salt. And remember, at the end point, I will be looking for that indicator to change color. Oftentimes with a strong acid and strong base, we use phenolphthalein. Phenolphthalein turns pink at a pH around 8. So you can see that is very slightly past the pH of the equivalence point. So we know that we've reached equivalence. And that tiny little bit past, you can see, is really maybe a drop or two to get from a pH of 7 to a pH of 8, which maybe means we're off by 0.05 or maybe 0.1 at the most on our volume. Out here at the end of this, I'll have excess hydroxide ions, so I'm literally back to just doing a stoichiometry problem with a limiting reactant. But at this point, my limiting reactant would have been the initial amount of acid, and my excess would be the hydroxide ions. So I have a very high pH. Now, the other option will be if I titrate a weak acid or base with a strong base or a strong acid. You really don't see weak titrations because it just doesn't make a good curve. The region of change around the equivalence point becomes really short and attenuated, and it's very difficult to read. So since there's not really any good reason to do a weak titration, people just generally don't do it. We'll generally do a weak with a strong, not a weak. Unlike in this case, we're not going to have a pH of 7 at the equivalence point because our conjugate salt that's being formed is not neutral. When we have a weak acid, remember we make a basic salt. And so at the equivalence point where we have just the salt left, that salt is basic. If I have a weak acid, remember that will form that stronger conjugate acid. So I will, at the equivalence point where all I have is the conjugate acid, I will have an acidic salt. And so my pH will not be 7 at the equivalence point. So let's take a look at a pretty traditional curve. I'm titrating a weak acid with a strong base. One, I can tell this because my initial pH is still acidic, but this would not be as low a pH as a strong acid solution, because a strong acid solution would 100% dissociate, where a weak acid is only going to give me a small percentage of the available H+ ions. At this initial pH, this isn't even really a titration problem. All I have in the flask is a weak acid, and that means that's just a Ka problem. I could calculate the pH using the Ka and solving for X. The minute I start titrating, though, once I start adding that strong base, then I am starting to make a buffer. And that means that in this region here, in between the equivalence point and the starting point, I am actually dealing with a buffer. I have both the acid and its conjugate that has been made by the reaction. And that means anywhere along this line, in between the initial point and the equivalence point, I can actually find these pHs using buffer math. I could use the Henderson-Hasselbalch equation, or I could use the H+ as Ka acid over base equation. I have a buffer in this whole region in between initial and equivalence point. One important point that we look for, though, is the half equivalence point. This pH is going to increase slowly because a buffer resists pH change. And at the half equivalence point, I have the critical fact where I have used up half of my initial acid. So half of my acid has been converted into base. And that means that if I look at my Henderson-Hasselbalch equation, or I look at the H plus as Ka acid over base, then the H plus is just equal to Ka, or pH is just equal to pKa. And that's a really important key point to know, that at the half equivalence point, the pH is equal to the pKa. That shows up for so many points because it's such an easy thing that people forget. That if I have this graph, I could find the pKa of this acid, and then the Ka of that acid, super easy. It's going to be like 3.95 or something like that, because it's just a tiny bit under 4. So I could find the Ka of that acid and then use that to find, say, the initial pH or initial concentrations. When I get to the equivalence point, I have used up all of the acid. That means there is no more acid left. Everything is base. And that means we have no more buffer. At the equivalence point, we no longer have a buffer solution. We have a solution of a weak base, the conjugate base. That means that's going to be a basic salt, and we'll use Kb math to solve that. The dominant species here is going to be A minus, the conjugate base of my weak acid, so that will be a basic salt. And we'll see my pH at my equivalence point of a weak acid being titrated by a strong base will always be greater than 7. The weaker the acid, the higher the pH at my equivalence point will be, because the more basic my salt. So this does go back to that same concept that we had back in the first part of this unit. We can't just say it's because it's basic. Well, no kidding. Its pH is basic because a basic salt is formed, and that means it hydrolyzes water and increases the concentration of OH minus. It's just the same as when we talked about hydrolysis in the first part of this unit. The weaker and weaker my acid, the initial pH is going to be higher and higher and higher for an equimolar solution, and the change near the equivalence point is going to get more and more and more subtle. So with a strong acid, strong base, I had that huge jump. With a weak acid and weak base, I'm going to get this slanting up through that buffer region, and then I'll still get that change, but it will be a shorter jump up instead of that huge jump up for a strong acid. Now, if I do use a polyprotic acid, in that case, we are going to have 2 equivalence points, because remember, at each equivalence point, we are dealing with 1 H at a time. So for example, here I can see the first 2 equivalence points for phosphoric acid. The first equivalence point takes off the first H. The second equivalence point takes off the second one. At this, really, you generally don't go ahead and titrate this on for the third one, because the Ka becomes so small and it's now such a weak acid that it really becomes almost impossible to see that third equivalence point. So we're going to look at the opposite situation now, weak base with a strong acid. Now I have a weak base in the indicator in the flask. I can tell because the pH is high. Again, this would not be as high as a equimolar strong base, but we're going to have essentially the exact same situation. I have the initial point is just a Kv problem. There is no buffer because I have not started adding any acid, so I have no conjugate acid. All I have is the insignificant tiny amount of conjugate acid I get from a Kv problem. Remember, those are often so small we consider those X's to be negligible. Once I start the reaction, I have this buffer region again, and now at the half equivalence point, I have POH is equal to PKB, or the pH is going to be equal to the pKa of the conjugate acid that I'm forming. At that half equivalence point, though, when I'm dealing with a base, I can remember POH is equal to PKB. At the half equivalence point, if I'm starting with an acid, pH is equal to pKa. At the equivalence point, you'll notice this is going to be less than 7 because the dominant species at the equivalence point is the conjugate acid. And a weak base makes that stronger conjugate acid that's able to hydrolyze water and create some H plus in solution. That means that this is no longer a buffer again. We have only the acidic salt, and it's hydrolyzing water to form the H3O plus ion. So in between the equivalence point and the initial point, I have buffer math. At the initial point, at the equivalence point, I absolutely do not. So just as a general mnemonic, a strong acid and a strong base, we make a neutral salt. The pH at the equivalence point is 7. A strong acid and a weak base, okay? Weak base makes an acidic salt, so I'll have a pH below 7. A weak acid makes a stronger conjugate base, so the weak acid will hydrolyze water with its stronger conjugate base, and the pH will be above 7. The last thing I want to talk about here is that when we are finding an indicator, this is where it's going to be really important that we can't estimate our equivalence pH, and we need to choose an indicator where the endpoint will be close to the equivalence point, ideally just a tiny bit past the equivalence point, because we know we want to have reached equivalence before we hit the endpoint. If we hit the equivalence point before the end, or the endpoint before equivalence, then we have no information to let us know when we really actually reached the equivalence point. So indicators have a varying pH range where that color is going to change. We want a sharp, clear color change just beyond the expected equivalence point pH. And a good estimate of your useful range is that the pH of your indicator is going to be about plus or minus 1 of the pKa. So for example, if I'm expecting, say, a pH of 8 because I am titrating a weak acid with a stronger base, then I might want to use thymol blue or phenolphthalein because the color change would be within about 1 unit of where my pH is expected to be. If I'm looking at something where I want to have, say, I'm expecting a pH to be below 7, if I'm titrating, say, a weak base with a strong acid, then I would not want to use thymol blue or phenolphthalein because those would change color too early. So just as a quick example, let's look at this last one. I have a pH at my equivalence point here at about, say, 5.25-ish. Not quite 5.5, maybe we'll say 5.25, 5.3. So I want to choose an indicator that's going to change color at a little bit less than 5.5 because I want to make sure my color changes after my equivalence point pH. So if we go back and we look at our chart, the only one that would work well for me would be methyl orange in this situation because all of these other ones change color too early. In this range, methyl orange would be the most successful one to choose because you can see the pH range of the color change is right about the pH range of what I would expect. And my pKa for my indicator is probably going to be right around 4.5 or 5 because it's going to be plus or minus about where the pKa range is about where the pH range is. You don't have to memorize indicators, but you do need to be able to choose the best one from a list. So for example, if I had this list and that situation, I would choose methyl orange as opposed to any of the other ones.